So the information theory in neuroscience, we have a bunch of sensory inputs like vision or smell and the hearing. But how does that sensory input, like how do we make sense of that? So how does the neural encoding and decoding tell us what the neurons tell us about the stimulus? Like related, and the different question is, how much does the neural activity tell us about a stimulus? And through this, the information theory kind of brings like a little bit of quantifications of part of the answer to this question, or at least tries to answer. So the Klaus Shannon is in 1940. He's the guy who came up with this theory of communication, or information theory. Develop information communication theory as a general framework for quantifying ability of coding scheme or communication channel to convey information. Like even just our language, it has like a lot of symbols, like a lot of symbols, and and like dog corresponds to like the actual dog with the 4 legs, and I mean it's just very complex too. And just like that, and there's no clear pattern in our language. Things are very random, and how they come about with the word itself is pretty, it's very random. It's hard to predict. There's no like pattern in that. Like 4-legged animals have like a word that they have it ends with like og, like dog. It's not then. Dog and hog, yeah, maybe they have 4-legged, but horses or cat, they don't. So kind of like that. So the coding and the transformation process is stochastic. So in some ways it's random, and it's kind of like has a lot of noise in it. So we have this concept of entropy and mutual information. So entropy, it refers to a theoretical capacity of code to convey information, and the mutual information is how much of the capacity is actually used when employed. So like we're referring to the quality of the information that's conveyed, like how much can be used. So communication channels, when they're noisy, have limited capacity. Information theory used to evaluate these limits and find optimal codes that approach capacity. Okay. So we are used to the idea of this entropy being this like being of order. But here we kind of tweak it so that it's referring to like how interesting and surprising the response is. So when the entropy is high, that means it's not ordered, right? And then if it's not ordered, that means it's hard to predict what will come next. And if it's hard to predict, then it's a surprising information. And that surprising information has a higher value in terms of information, right? And in the other way, if there's a low entropy, then it's predictable. And if it's predictable, then the value of the information, or the information itself, is not much. So low entropy is low information, and high entropy is a lot of information. And then here we define the entropy as this H, and that this PR is just the probability of this neuron firing. And so negative log to base 2 probability of R. And if I draw this graph. So x-axis is the probability of R firing, and the y-axis is the entropy. So this is showing the negative log to x. And as we see that as the probability of neuron firing approaches 1, so 100%, the entropy becomes 0. So like we already know, it's not surprising, right? And on the other hand, as the probability of neuron firing goes to 0, the entropy like approaches to infinity. And because when the entropy is like the probability of firing was like 0, but if it had fire, which is unexpected, then the value of the information, or the entropy, is very high. And this Shannon's entropy kind of normalizes or by having this probability term instead of multiplying by this log term with the probability itself again. So if we go back to here, so they have like the negative correlation. So when this log term is trying to get bigger, we also multiply by which when this log is trying to get bigger, that means the probability is getting small, and by multiplying the log term with the probability, which is small term, we kind of like contain or normalizes it in a sense. So the entropy is so if the probability goes to 0, then the entropy goes to infinity. But if we actually like do the thing so the limits approaches 0, because this, yeah. So a response with low probability may contribute little despite having a large entropy, because it's multiplied by the small probability. And so if you think of it for the coin flipping example, so let's say this is like head, then the probability of, if we always get like head, which is 1, then the h will be 0, as we have seen in this example. If there's 1, the h is 0. And then we can expect the same thing over here is 0. So the probability of head for the coin is 0. That means it's always tail, and it's expected. Then so we will have 0 on here. And in the middle, we will have a higher entropy with the value of information, or the amount of information. So that's why we have this. And if you actually kind of put it into like the equation, so that the entropy is equal to negative p probability of head times log 2 base 2, and the times probability of head minus this term, and we will get the maximum value at this the probability being equal to 0.5. So the mutual information is I, we have shown as I, and so the entropy R minus entropy R given S. Here they're referring to response and stimulation for R and S respectively. So this makes sense because if there's absolutely no correlation between R and S, the response and stimulation, then the entropy given R, entropy of R response given S, given the stimulation, will be identical to the entropy of response, and that will make this mutual information goes to 0. And we do the similar thing with the probability of R timing times the log term. Similar thing going on here, but the difference is that it's R given S, and we also normalize by R given S probability. And then we get the term like this if we do the math. And this is important because it's trying to, this is the part that kind of answers how close are these probabilities, or how close are they dependent, how correlated are they. So here the probability PRS is the probability of R, the response and the stimulation both happening at the same time, and then this is probability R times probability of stimulations. So if they are like interdependent, then this PRS and PR, and the bottom term will be identical. It will be 1, and the log 1 is equal to 0, and this whole mutual information term will go to 0. But if they are not dependent, then there's a difference in or if they are dependent, that R and S will happen at the same time, it will be higher than the probability than this. So it depends on the dependency. And this is kind of like similar thing, just written in different format. The callback and labeler divergence. So we can measure the different. What we're measuring the difference or distance between the p, the probability of s given r, and just probability of s here. So one thing. So we're still like struggling in neuroscience, struggling to find the theory that explains the brain system. In biology, there's a natural selection theory, but for neuroscience, we kind of don't. So one of the theories, the information maximization theory, is that we're trying to maximize the information processing, and that's how this brain works. But it comes with the cost of, the metabolic cost of ATP or something else, like to be able to send the information from like this one end of the brain to the other side of the brain. Like there's cost to of sending it. If they're more closely located, they would have less cost, and so on and so forth. There's a lot of optimization that needs to happen. Now the question is, like, why, when we observe different animals' brain structure, like we can ask the question as like, why are the things the way they are? But we are uncertain because are the brains situated like that because of the current environment, or is it a remnant of the previous environment that we're talking in terms of the evolutionary scale, like a macro scale, like thousands of millions of years ago, kind of like the human's tailbone. So this is a great grandson of Charles Darwin, Horace Barlow. He's a big guy, and he's the guy who supported this efficient coding hypothesis that we are trying to make brain works in a way that tries to maximize the information processing, and while trying to make the resources usage as efficient as possible. And this hypothesis are breaking into two components, or composed of two components: statistic of individual neurons and joint statistic of the population. But one thing that bothers me is the response of different neurons to natural environment statistically independent from one another, but very dependent. So, oh well. So here, coming back to the entropy, which is referred to as a value of information over the amount of information, so we're trying to make this entropy as big as possible for the signal, but we're trying to minimize the noise entropy as right. So you want to find FR that maximizes this function, that maximizes the entropy, and we kind of show it as here. And the density this is a density function, so they got to integrate to 1 into the mass. We get that. So we feed in this stimulation with the density function, and then we go through this black box, and we get this response out. So we have this density function of stimulation, and then we had this is a random Gaussian distribution, but if you were to see the response, it got to corresponds to something. It has got to show a clear trend. So what I mean by it, it's like this is the random, but then the output O, we want to see like this. Like this is what we're trying to see. So like how do we need a way to convert that or transfer that. And so they have this like theoretical function that like does it, and they showed which is the black line is the theory, and then this dot is experimental data, and it kind of like follows. So that's cool. And this is a top view of like monkey like doing its thing, like because it's like making decisions. So we think or we sense something, then we go through cognitive function of deciding what to do, and then we actually move. So this is like the setup, monkey moving things, arm, and the top view of it. And then we get something like that. In each direction, the neuron fires a little differently, and it's kind of like neurons are like voting, right? Each neurons are say, oh, we're trying to go left, or we're going to the top, to the right, but they, as a group, they reach a consensus, a vote, and then decide to move to a certain direction. And this is another experiment where monkeys have this fixation point on one thing, and then they display something, some dots somewhere, and then they move into a certain direction. The monkey has to point at the direction that the dots were moving. So it's kind of like a game. They're really great at it. So at 0% coherence, the dots are like just going to random directions. So there's no direction. 50% coherence, and the 100% is everything's going to one direction. And surprisingly, monkeys are pretty good at it. And so neuronals is referring to like the just measurement from this one neuron. The behavior is the behavior of the monkey itself. And we see that like despite for a fairly wide range until like 1% coherence, like we see like really good correct high rate of right answer. So this neuron, what we see is that if even though it was just one neuron recording, it kind of like they kind of went hand in hand in terms of its behavior in the neurons. So they're basically like this monkey and the neurons are kind of like one, and they're like together. This is just shows like so it's just like the left or right or top and bottom motion. So just and when the coherence is like very different, if you see that black refers to maybe left and white refers to like right motion, they're pretty different. But as the coherence like decreases and they become assimilated, their firing rate of the left neurons and the right neurons are like similar. Yeah.